I'm going to talk about hyperquaternions, an efficient mathematical formalism for geometry. This is a collective work with Romaric Pujol, Patrick Clarysse, Robert Goutte, and Philippe Delachartre. This work is done at Clarysse Laboratory of Imaging. Here's the outline. We first give the background, quaternions, hyperquaternions, and multivectors. Then we go on to pseudo-orthogonal rotations, a few definition theorems. We give a canonical decomposition in the hyperquaternion formalism. Then we go on to the Poincaré groups in n dimensions via dual hyperquaternions. And then we end up with a 5D Poincaré group example. First, quaternions. Quaternions are a set of 4 real numbers which multiply according to the famous formula I squared equal to j squared equal to k squared equal to ijk equal to -1, which is going to be the cornerstone of all what we are going to do in this formula. The product, you just develop this algebra, and you have the product, which here is expressed in terms of the scalar product and a vector product, but it can be presented differently. We define the conjugate of a quaternion, okay, with the property AB conjugate is equal to BC AC. Hyperquaternions we shall define as a tensor product of quaternion algebras. The subalgebras thereof are complex numbers, biquaternions, Dirac algebra, etc. The tensor product is very easily defined and uniquely defined. We just take a system of commuting quaternion systems. So we call, for example, ijk we call we call small ijk the first quaternionic system, capital ijk the second quaternionic system, and LMN the third quaternionic system. This system commuting with each other. Okay, so the tensor product is its usual one. We get a simple notation. For example, tensor I is just I, capital I, L. Okay, this can be implemented immediately on any machine. So the product is defined in our.
So what is J? There is a J.
Yes, we have ijk, which is a quaternionic system. Some people have perhaps never heard about quaternions. Okay, so I come back to the other slide. So complex numbers.
The big J, I mean.
The small j is here.
No, but the big J.
Yes.
You have a product, you have a big J.
Yes, the big J.
ijk equal to I big J n. What is big J? Here.
So
yes.
Here, the tensor, the small j here becomes a capital J here. But it's the second quaternionic system. Okay, it's just a notation here. Okay? We have a product of commuting distinct quaternionic systems. Okay, it's just tensor product. Is this okay? Then we define a hyperconjugation. We have defined the conjugation for quaternions, and we take this definition of the hyperconjugation. What we get is the hyperconjugate of this gives the transpose, the matrix transpose, and here we have an important property. H, tensor H, is equal to 4 square matrices, which is well known. Okay, it's a well-known isomorphism. Okay. So we get here HHC, which is M4C, and HHH, which is M4H. So here we get all real complex and quaternic matrices. So we have a huge mathematical range for hyperquaternions. And what we have here, we have the transposition here for the real matrices. For the complex, for this hyperquaternion, we have the adjunction, and then we get the transpose conjugate, which is used in unitary symplectic groups and so on. Hyperquaternions are not only all real, complex, and quaternic matrices, they are also isomorphic to Clifford algebras. And that's the main point here. So what are Clifford algebras? They are generated by n generators which anti-commute. Example, take for example the biquaternions, HC. We take 3 anti-commuting generators which are going to be vectors. And this choice induces a multi-vector structure of the algebra. So here we get bivectors, which are going to represent planes, torques, and so on. We have trivectors, which are going to represent 3 volumes, and we have scalars. So we call the scalars the V0, vectors V1, that is, we take just this part, bivectors, we just take this part, and trivectors, we just take this part. So in the same algebra, we have all the different components of physics, of the 3D physics. Then we define the conjugate in the general case for a hyperquaternion. EI is replaced by minus EI, and we reverse the order of elements. So we get this property, and we have ABC, etc. We define the dual of A, which is A star, which is ID multiplied by A, and here we have an exterior product to be defined later on. We define also the commutator of 2 hyperquaternions like this. Then we define interior and exterior products. We have defined the multiplication. If we take 2 vectors, if we multiply 2 vectors, we have this identity, and we get a scalar and an exterior product AB. So the scalar is given by this, simply, is defined by this, or we just take the V0 part of AB, and for the exterior product of 2 vectors, we have just V2AB, or defined like this. We are going to use essentially products between bivectors. So if we multiply bivectors, we get a scalar, we get an exterior product, and we get here a commutator, which is a bivector. So to get these products, we just take the corresponding part. And if we need a product like this, an interior product between a bivector and an exterior product of 2 bivectors, we just take the bivector part of this. So all these interior and exterior products are well defined and easily obtained. So now we have defined our hyperquaternion formalism and the geometry behind. The important point here is that the exterior product is associative. Okay. And so here we are going to be able to represent geometry in whatever dimension with an exterior product and interior product. We go on to pseudo-orthogonal rotations. We start from a hyperquaternion algebra, which is of the type CPQ. With a matrix, we have defined the vectors. We get the matrix, which is the pseudo-orthogonal matrix in the general case. Okay. We have time-like vectors, we have space-like vectors, and we have isotropic vectors. Okay. An orthogonal symmetry is just with respect to a plane going through the origin and perpendicular to unit vector A, is given by this simple formula, plus or minus AXA, where A is a vector, X is a vector, and A is a vector. So we get immediately this. We have an orthogonal symmetry. And we use Cartan theorem, which says that every rotation is a product of an even number 2m smaller or equal to n of symmetries. we go on to the special orthogonal group, SO plus PQ, which are the rotations which preserve the orientation of the spaces of positive norm and of negative norms. And we get the simple formula, okay, for rotations in any dimension, which has the same simplicity as the rotation formula, the quaternionic rotation formula in 3D. So the A from via the Cartan theorem is expressed as a product of vectors. And it's an element of C plus, that is, it's an even number of generators. It's a product of an even number of generators. Okay, with an even number of time-like and square space-like vectors. So if we develop the product of two vectors, we get a scalar and a bivector. Now, this bivector, it's a simple plane. That is, it's defined by B exterior B equal to 0. Okay, because if we make an exterior product, we have two vectors which are the same, and so it's 0. So a rotation involves at most m inferior or equal to n over 2 simple planes. Then we go on to the canonical decomposition of rotation. One chooses these planes to be orthogonal and commuting. So what we want is to express A, the factor A which we have developed, as a product of exponential where B1, B2, Bn are orthogonal, simple commuting planes. So we get these properties. We have Bi, Bj, the scalar is 0. And we have Bi, Bj, which is Bj, which commute. And we have Bi, Bj, which is an exterior product of two bivectors. All these formulas have immediate physical meaning. The phi you have here is just the angle of rotation within the plane Bi. So we get, here we are in a hyperbolic geometry. So if B1 Bi squared is equal to -1, we get the usual cosine sign. And if we have Bi squared which is equal to 1, we get here a hyperbolic cosine and a hyperbolic sine. So a rotation is expressed by this. We have Bi which corresponds to this, or tangent, hyperbolic tangent, and we can develop A like this. Okay, in terms we just develop here, we get we have B1, these are by vectors, and so we get this expression. So AAC is equal to 1, and so we get S, the scalar which we have here. Look at this here, the scalar which is here, which is expressed in terms of the Bi, the small Bi squared. And if we develop the A completely, we get S, and we get an exterior product of bivectors. Okay, so the rotation is completely determined by the bivector B. How can we get the coefficients Bi and the bivectors Bi? Canonical decomposition has already been introduced a century ago by Moore, 1918, for the Euclidean case. And here we extend this solution to pseudo-Euclidean spaces, and we implement this within a global hyperquaternionic framework. So the rotation being determined by the B, we have the B here, and we make a change of variables. So let me come back to this. This is very important. Look at this formula. The rotation is supposed to be given. We have the B. Our problem is to find all these quantities, the coefficients and the planes. So we make a change of variables. We have xi, we have a new variable here. We have small xi which is equal to xi squared equal to this. We develop these equations. Okay, here we have an exterior product and an interior product. Exterior product, interior product, we compute all this. And we get a linear system in xi. The coefficient being not known for the moment. So we have a linear system. We just solve this linear system. Okay, so we have a delta, which is expressed like a product of the lattice. If delta is different from 0, one obtains the bivector as a function of Pm and xi, the Pm being known. If delta is 0, the equations are not independent. The bivector can nevertheless be decomposed in m mutually orthogonal simple planes, but this decomposition is not unique. How do we get the small xi? Well, we just write equations like these. We have scalars here, p1, p1, p2, p1. Let me come back here. P1, this is just these quantities here, okay, which are well defined. So we compute these quantities, and here we have we have not a linear system. We have a system of equations which we can solve. Okay, which the solution is known. We can solve these equations. So the solution out of this, we get the small xi. So we get the bi, and then we have the xi. Then we get bi equal to xi over bi. So here we have a canonical decomposition of pseudo-orthogonal rotations in n dimensions, in whatever dimension. Let's go on now to the Poincaré groups. Much of physics is just a representation of the Poincaré group. Okay. And here we introduce dual hyperquaternions. So we start from a general hyperquaternion. We have a certain hyperbolic matrix. And the Poincaré group includes the rotations, which we have just spoken of, translations and reflections, etc. We are going to deal only with the rotations and translations. So we start from a hyperquaternion algebra and we introduce, we want the Poincaré group in n dimensions. We add one dimension. So we take a hyperquaternic algebra with n plus 1 generators. Okay, we add one generator and we take the corresponding algebra. And we introduce a dual vector like this. This is the extra dimension and epsilon x, where x is just a vector in n dimensions, and we have epsilon squared, which is 0, and commuting with all the rest, with all other quantities. Now, an ND hyperbolic rotation in V1, okay, in the n space, leaves the last variable unchanged. So we get this formula for the rotation, AXA, like this, where x prime is just equal to AXAC. And we get conservation of the norm, etc. Yes? 2 minutes. So we express the translation. And we can express this as an exponential like this, okay, t over 2. And we verify that this is indeed a translation, okay, on all the n variables. Okay. A combination of ND rotation and translation gives a general f, okay, and then we can apply to this f the same canonical decomposition we have just introduced. Example, a 5D Poincaré group. For example, you have a 2D image, color image. You have 3 color spaces, 3 color dimensions, 2 D spaces. We have a 5D space embedded in a 6D algebra. So we take our generators here, and we start, for example, with a certain f. Okay, we combine rotations and translations, and then we decompose. We apply the canonical decomposition, And we find immediately the different planes. Okay, and here we have planes. We have planes with b squared equal to 1, and we have also planes which are equal to the square is equal to 0. Conclusion, what did we do? We have introduced the Quaternion, hyperquaternion calculus. We have given a hyperquaternion representation of pseudo-Euclidean rotation and of the Poincaré groups in n dimensions. We have given a canonical decomposition. We have given a 5D example. Potential applications are moving reference frames and machine learning. That is, for machine learning, for example, you can use symmetry groups, and this Quaternion CNN have already been used, have already been presented in the literature. And so the idea is to use symmetry groups instead of taking arbitrary coefficients. Thank you very much.
Thank you. Questions? No questions? Yes.
What is the application?
Applications, yes. For example, if you have an image, you are going to use the Poincaré group. You are going to have rotations and translations. Okay. And so instead of just taking arbitrary convolution coefficients, you can take symmetry groups, like rotations and Poincaré groups. Okay. And so the idea is to apply this eventually to machine learning. And of course, we have all the moving reference frames, which are a huge application. So here, this is a new way of doing geometry with potential applications for machine learning and so on.
Okay, let's thank the speaker again.